Hello, my name is Anthony Pepitone, and this is Lab 5, the Following Slinky. Before we get into this lab, a brief overview. We're going to be tracking the motion of the bottom of Slinky after it is dropped. We will be able to do this using Tracker and being able to plot the data of this motion. After that, we're going to be creating a code to model this motion. And lastly, we're going to be comparing the modeled motion and the motion from the real video. As a brief preview of the result, the bottom of the Slinky is not going to move until it is reached by the top. Now, let's look at some key formulas and equations for this lab. First of them is going to be Newton's second law, which is velocity final is equal to velocity initial plus F net over m times delta t. Along with this, we have the F net, which is going to be equal to the force of gravity plus the force of drag plus the force of Slinky. We're going to be using these two equations primarily to find the velocity updates and the positioned updates of the Slinky along the way. For the gravitational force, we're going to be consistently using negative mg. For the drag force, we're going to be using negative v squared times v hat. And lastly, for the Slinky, we're going to be using the tension force. And the reason we use this tension force is to take into account that the bottom of the Slinky is not falling until the top has reached it, which means there must be some sort of tension force acting in the opposite direction of gravity throughout this lab. Before we look at the video, our system is the Earth and the Slinky, and our surroundings is going to be everything else. And for the initial conditions, our Slinky's mass is going to be 0.25 grams, and the starting position is going to be 0, 1776, 0 meters. Now we can look at the motion of the Slinky. And as we can see, the bottom of the Slinky does not move until the top has gone all the way down to meet it. This code is going to be split up into two parts. The first half is when the bottom of the Slinky is not moving, and the second half is after the top has fallen and the bottom of the Slinky starts to move. For the first half, we're going to have W, which is equal to negative mg times j hat, and Ft, which is the tension, is equal to mg times j hat. These forces are equal but opposite, and therefore when they get added together to give us F net, there is no force or any movement of the bottom of the Slinky. The second half, after the top has reached the bottom, is going to be the same W of negative mg times j hat, but rather than Ft, we're going to have Fd, which is the drag force, which is equal to negative b times the magnitude of the velocity squared times the ball velocity. These added together will give us motion in the negative y direction, showing that the bottom of the Slinky is now moving. As we can see in this graph, the experiment versus the model predictions of this experiment are quite similar. However, there is some discrepancy, and this could be due to possible sources of error, such as plotting the tracker points or accounting for other forces that may be taking place on the Slinky throughout the video. What does this all mean? Because the bottom of the Slinky does not move until the top has reached it, we can see how tension and gravity are balanced. The Slinky in itself has a tension force, which is exactly equal but opposite to the gravity force. Therefore, when added together, these result in an F net of 0, which shows why the bottom of the Slinky does not move. However, after the top of the Slinky has met the bottom of the Slinky, there is no more tension force and rather just drag, which is a little less than gravity, resulting in the Slinky being able to move down while only having some resistance along the way.